All right, today we are looking at two new reactions, SN1 reaction and E1 reaction. Before we talk about either of these reactions, I want to mention something about a reactive intermediate called the carbocation. It turns out the carbocation is involved in both the SN1 and the E1, so we need to talk about it first. Okay, so let's go ahead and write it out. Carbocation. And carbocations are very important in organic chemistry because they are a very common, and the word I used was reactive intermediate. Okay. A reactive intermediate is an unstable molecule that's present in organic mechanism. It actually doesn't have to be organic. We have reactive intermediates in inorganic chemistry too. But for the purposes of this class, it's an unstable molecule that's involved in a mechanism. So what is the carbocation? A carbocation is formed when carbon has 6 electrons. Thus, they are high energy because they don't have a full octet. And there's a few different flavors of carbocations, and although they're all unstable, some are more unstable than others. So let's rank their relative stability. Okay. The worst carbocation you can have in organic chemistry is the methyl carbocation. It's formed when you just have carbon with 3 hydrogens attached, and the carbon has a plus charge because it only has 6 electrons. This is called the methyl carbocation, and it is the worst. And the reason it's the worst is that the carbon has only 6 electrons, and the hydrogens don't do anything to help it. The hydrogens are not electron releasing. They are just sort of doing nothing. The carbon is there struggling, suffering, wanting 2 more electrons, and the hydrogens have nothing to do for it. A little bit more stable than that, but still terribly unstable, is the primary carbocation. A primary carbocation has one of the hydrogens replaced with a carbon. In this case, I'm replacing it with a methyl group, but it could really be any carbon chain. And this is slightly better. It turns out that carbons are electron releasing inductively, so they can release some electron density towards this electron deficient carbon and help stabilize it. Okay, so carbons are electron releasing. So this is primary, and it's oftentimes abbreviated with the 1 degree symbol. And it's a little bit more stable than methyl. And I think you can imagine what's coming next. It's the secondary carbocation, which is considerably more stable, but still, you know, we're talking about carbon without a full octet. These things don't last very long. They're very high energy. This is the secondary one. This is when 2 of the hydrogens of the methyl are replaced with carbon. And then considerably more stable than that is tertiary. That's when all of the hydrogens are replaced with carbon. It's called tertiary, and that is the more stable of them all. Okay? Now, it turns out that there's something even more stable than tertiary. You might say, how's that possible? We can't add another carbon, otherwise then it wouldn't be a carbocation. Then you'd have 4 groups, it'd be normal carbon. But we can add something else. Okay, so let's continue our order here, and we're going to talk about resonance now. Okay, resonance is super stabilizing. So even more stable than tertiary are resonance stabilized. So I'm actually going to continue. So here's tertiary. Even more stable than tertiary is something called allylic. Allylic is when you have a pi bond next to the carbocation. That's called allylic. Allylic comes from the Latin word allyl, which means garlic. So it turns out that the garlic plant has a lot of double bonds in it, and so it got made a name that's associated with garlic with that structural pattern, which is the allyl group, which is named for garlic, where it's found very commonly in those spicy garlic compounds. So allylic means garlicky, but really what it means is carbocation next to a pi bond. Remember, not part of the pi bond, but next to it. And it's stabilizing because there's a resonance structure that can occur to help, what's the word I'm looking for? Disperse. That's the word. Disperse the positive charge among multiple atoms. Okay. That is a little bit less stable than the benzylic carbocation, which is like a special form of allylic. And it's when you have the positive charge next to a benzene ring. This is called benzylic. Okay, and that's obviously super stabilizing. There's a lot of resonance structures possible. You can move this pi bond, you can move that pi bond, you can move that pi bond. So it's like allylic, super allylic. There's something even more stable than benzylic. It's heteroatom stabilization. So if you have a lone pair, like OH group here, next to the carbocation, that is the most stable situation you can have because there's a resonance structure that actually completes the octet. All these allylic and benzylics, those disperse the positive charge, but only the heteroatom one can actually quench the positive charge. So this is heteroatom stabilized. All right. So let me show you an example of a quiz question or a test question that you might get. Something like, example, rank the following carbocations. From least to most stable. Okay, so let's do methyl. This one here. Right there. Okay, there's 5 carbocations. Let's rank them from 1 being the least stable and 5 being the most stable. If you want to try and pause and try this on your own, go ahead and pause. Okay, you had a chance to pause. I'll tell you the answer now. So the least stable is going to be the methyl. Methyl is always the worst. Okay, and then next up we're going to have our secondary carbocation, which is bad, but a little bit better. Then comes the tertiary carbocation. Better still, there's 3 carbons attached to that plus charge. Now it's between these 2 allylic carbocations. Which one of these allylic carbocations do you think is better? That's right. This is a better allylic carbocation than this one because this one is tertiary and allylic, but this is secondary and allylic. So that means this one is the best and this one's second best. Okay, so that's an example of a test-like question that will maybe pop up on midterm 3. All right, so now that we know about carbocations, let's actually talk about SN1 and E1. Obviously, the carbocation is involved in both of these reactions. So, intro to SN1, E1. Okay, let's first start with SN1, and let's do an SN1 example. SN1 typically starts with a tertiary substrate. Those are the best. And the reason is that secondary and primary substrates don't stabilize carbocations very well, and we'll see that that's important in the mechanism. It's also interesting to note that the tertiary substrates are really bad at SN2, so that makes SN1 a nice complement to SN2. Another key feature of the SN1 reaction is really weak nucleophiles. The nucleophiles are typically neutral. They're things like methanol, ethanol. Basically, all the nucleophiles that are way too weak for SN2, they work fine for SN1. The product is substitution, just like SN2. We're going to now replace our leaving group, bromine, with OMe from the methanol. And then we're going to generate a byproduct of HBr, we'll see how that happens as well. Okay, let's take a look at a generic example of an SN1 reaction, just to make it as generic as possible. We have a carbon attached to a leaving group, and the carbon is sp3 hybridized, must be sp3 hybridized, just like all the other reactions we've seen so far. They don't work with sp2 or sp. It needs to be tertiary or secondary, generally speaking. No primary or methyl. Okay. We are going to add a weak nucleophile. The nucleophile is typically neutral, and it's typically used as solvent. So weak nucleophile, typically solvent. So although the nucleophile is very weak, we do use a lot of it, so that there's like relative to our substrate, a huge excess of the nucleophile, and that's why we use it as the solvent. It actually dissolves everything. And then the product is going to be the carbon is now attached to the nucleophile, just like a substitution reaction, plus H attached to our leaving group. Okay, what is the mechanism of this transformation? Now, even though the name is SN1, the mechanism is actually 3 steps, which is kind of, be careful, the SN2 reaction is only 1 step in the mechanism. A backside attack followed by leaving of the leaving group. This mechanism for the SN1 is actually 3 steps. So step 1 is called dissociation. Step 2 is called nucleophilic attack. And step 3 is called acid-base reaction. Okay. All right, let's watch the mechanism of this process. So we'll start with our example from above, our tert-butyl bromide. And the first step is dissociation. Dissociation is the leaving group just leaves on its own. And this is typically an equilibrium process. So the leaving group can leave, and they can come back, and can leave and come back. But when the leaving group leaves, it takes the electrons with it and leaves behind, you guessed it, a carbocation. So this is the carbocation intermediate. And that explains why we only like secondary or tertiary only. Because remember, the carbocation stability increases with secondary and tertiary substrates. Now, obviously, allylic, benzylic, and heteroatom stabilized, that's really good for SN1 because those carbocations are very stable. So you can imagine the more stable the carbocation, the more favorable this equilibrium will be towards the right. Now, no carbocation is going to be as stable as this. So the concentration of carbocation is always going to be extremely low. But the more stable the carbocation, the more likely the reaction is to occur, period. Okay, now when that happens, the bromine is still hanging out. And there's possibility for the bromine to simply come back and recombine with the carbocation. And if that happens, it goes back to the starting material. And that happens from time to time. However, we have our solvent, our weak nucleophile, as methanol in this reaction. And this kind of explains why the solvent is important, why the nucleophile is typically the solvent, because even though the nucleophile is weak, if it's present in large amounts, it can outcompete the bromine and attack the carbocation with its lone pairs. This is called the nucleophilic attack step. Once that occurs, we've created a new bond between the methanol and where the carbocation once was. And we end up with this substance here. Now, another molecule of our alcohol or of our nucleophile comes in and performs an acid-base reaction to remove that pesky proton to give us a neutral product, and that's why we end up with this. We end up with our ether product and the byproduct, which is our protonated alcohol. Okay, and then the protonated alcohol can further react in an equilibrium with the bromide. It's possible that the bromide would take the proton away from the... You don't have to draw this step. It's totally optional. All I care... You can just stop right here. But I think you were just probably wondering, how is the HBr made? Well, the bromide could react with a protonated alcohol to give HBr. Plus the methanol back. Okay, but that's you don't have to show that step. Okay, this is really what I want you to focus on, is this part right here. Dissociation, nucleophilic attack, acid base, and then just stop with the product. That's the mechanism. So let me show you a cool little cartoon I found that sort of illustrates the difference between SN2 and SN1. So these are the two kitties. And I've got, I don't know if you guys know this, but I've got two kitties, but they're staying with their parents right now. And with my parents. And I have one kitty named Finn and another kitty named Kashmir, who's gray. Okay. And Finn is kind of the dominating cat. And so in the SN1 reaction, the scenario is that Kashmir gets bored of his bed and he steps out, and then Finn goes into the bed where Kashmir was. That's an SN1 reaction. Dissociation, this is the leaving group leaving, and then the nucleophiles coming in. In an SN2 reaction, that's much more aggressive. Kashmir is still attached to his bed, but Finn jumps in and displaces using backside attack, kicking out the leaving group at the same time that the nucleophile comes in, and then this outcome is the same. In both cases, the outcome is the same. So what we can see here is that the starting point is similar for both SN2 and SN1. The outcome is similar for SN2 and SN1, but how the reaction occurs, that's where the difference is. SN1, first the leaving group leaves, then the nucleophile comes, versus SN2, they both leave and come simultaneously. Sorry, Kashmir. What we can do to also illustrate this is draw something called a reaction coordinate diagram. You probably saw this at some point in your chemistry career. And I promised earlier that I would explain why SN2 is called bimolecular and SN1 is called unimolecular, that the 1 and the 2 part of SN1 and SN2. And the reaction coordinate diagram will allow us to see that. The reaction coordinate diagram is a plot of reaction progress versus energy. Okay, so let's take a look at the SN2 reaction coordinate diagram. So I'll just draw like an XY plot. Some people love these diagrams. I never got too excited about these, but it's kind of cool to think about. And so the y-axis is energy, and along the x-axis we have something called the reaction coordinate. This is just a way of sort of arbitrarily plotting the progress of the reaction from reactant to product. And so in an SN2 reaction, it's one step. It's one step. And so we have our reactant here at the beginning of the reaction coordinate diagram and our product here, the end, the reaction coordinate. And the way the reaction looks like is kind of like this. I'll make it a little bit smoother. There we go. And right at the very top, the highest point is called the transition state. Transition state is the highest point between two materials, two molecules. The peak, if you will. And if you remember, the transition state of the SN2 reaction looks like this. I'll just draw kind of a generic transition state. We have a carbon in the middle that got kind of flattened out. We have a leaving group that's leaving, call this bromine. We have a nucleophile that's coming. And we have this double dagger thing to symbolize that it's the transition state. We can also draw some partial charges, that the nucleophile has a partial negative charge as it's coming in, the leaving group has a partial negative charge as it's leaving, and the carbon in the middle is partially positive. So that's a transition state for the SN2 reaction, and that's where we are right at the top of our peak. Okay. Now let's look at the SN1 reaction. The SN1 reaction. The SN1 reaction is 3 steps. Energy here. And reaction coordinate. Okay, and the way this looks is we've got our reactant and our product just like before, but the path to get there is different. I'm going to go through multiple transition steps. Transition states, I mean. There we go. We're going to have 3 different transition states. And in between the transition states, we have intermediates. The intermediates are the little dips in the peaks on the way in between transition states. So the SN2 reaction has no intermediates, but the SN1 reaction has 2 intermediates. So these are intermediates here. And we have 3 transition states. Transition state 1, transition state 2, transition state 3. Okay, let's just draw transition state 1. The first step of the reaction is dissociation. And as you can see, transition state 1 is the highest energy transition state, which this means it is going to be the rate determining transition state, the most important transition state for the rate of the reaction. In other words, once the reaction has enough energy to go over the first hump, it'll have enough energy to go all the way down to products. So it's the slow step. It's the step that's going to determine the rate of the reaction. And if we look at the transition state for the dissociation step, which is the first step of the SN1 reaction, it's just going to be the leaving group dissociating. So we have our nice little molecule, and the leaving group is just leaving. And we can draw some partial charges there as well. We have delta minus on our bromine, delta plus as our carbocation is forming. There's our double dagger to indicate this is a transition state. And then we can also draw intermediate 1. Intermediate 1 is just our carbocation. Okay. Now, let me just put a little in writing so that we can be clear here. So transition state 1 is dissociation, the first step of our mechanism. And what I want you to look at is the highest energy transition state for the SN2 reaction and for the SN1 reaction. Let's look first at the SN1 reaction, highest energy transition state, which is transition state 1. Which molecules are involved with transition state 1? The substrate, the nucleophile, or both? Well, look at transition state 1. It's just the substrate. The nucleophile is not in the picture. In other words, the slowest step, the highest energy step, dissociation, only involves the substrate. The nucleophile is not even in the picture yet. So rate relies on substrate only. Nucleophile isn't even in the picture yet. Okay. The nucleophile isn't even in the picture yet. Now look at the SN2 slowest transition state, highest energy transition state. There's only one of them, so it is the highest energy one. Look who's involved with the highest energy transition state for SN2. Both the nucleophile and the substrate are involved with the highest energy transition state. So, number of starting materials involved in highest energy transition state determines molecularity of reaction. Okay? So since the highest energy transition state of the SN1 reaction involves only one starting material, the substrate, it's a unimolecular reaction, and that's why it's called SN1. In the SN2 reaction, two molecules, two starting materials, are involved in the highest energy transition state step. So it's a bimolecular reaction, and that's why it's called SN2. And if there was a possible SN3, then there would be three starting materials involved with the transition state. So for the SN1 reaction, there's one molecule involved in the starting material, so SN1 is what we call unimolecular. the rate depends only on the dissociation. Doesn't matter what the nucleophile is, it won't affect the rate. And what that means is if you used a super strong nucleophile, it wouldn't affect the rate of an SN1 reaction because the SN1 reaction doesn't care about the nucleophile. The only thing the SN1 reaction cares about is how fast that leaving group can dissociate. And what affects how fast that leaving group can dissociate? Well, the stability of the carbocation is one thing, right? If you stabilize the carbocation and make like a allylic carbocation or benzylic carbocation, you're going to bring the energy of the transition state in the first intermediate down. That's going to help you speed up the SN1 reaction. Okay, enough about the rate. Let's talk about some SN1 details. Okay, first important detail we need to talk about, very important detail, stereochemistry. Okay, what about the stereochemistry? Turns out that SN1 is not stereospecific. Let's take a look at an example of that. Let me draw a nice chiral molecule here. Put a methyl group here. Put a chlorine here, a methyl here. And let's do an SN1 reaction with water. Okay, in the first step of the SN1 reaction, the leaving group is going to dissociate. Just leaves on its own and generates a carbocation. Okay. And I'm going to try and kind of draw this in 3D if possible. Kind of draw it kind of a side view if you can see that. Okay, and so the methyl group is going up. And there's a hydrogen going down on this carbon, not shown, the implicit hydrogen, but I'll draw it in now. And then the carbocation forms at this position. The carbocation sp2 hybridized, it's flat. So the methyl group kind of flattens out because sp2 hybridized is trigonal planar. And now we have an empty p orbital on this carbon. And this is our carbocation right here. Okay, so although we had stereochemistry in our starting material, after the leaving group leaves, the hybridization changes from sp3 to sp2. And when we have sp2 hybridization, it's perfectly flat. There's no more wedges or dashes. Now the water, which is our nucleophile, can attack this carbocation either from the top or the bottom. There's no preference. It does so with 50-50 probability. So 50% chance to attack the top versus bottom. It's completely random. So what that means is that the product is random. The stereochemistry becomes randomized, and we actually get two products out, which happen to be diastereomers of each other. So the first product that we get is when the water molecule, and I'll skip the acid-base step, but there would be an acid-base step that deprotonates the H2O. But the stereochemistry on the left is not going to be affected. But the water could even either come from the top, or the water could come from the bottom, in which case the OH would be dashed, the methyl would be wedged. So can you see how the stereochemistry on the right carbon is randomized after the SN1 reaction? By the way, when you get a 50-50 randomization of the position, there's a special word for that. It's called racemization. Racemization is the name for randomization of a stereocenter in an SN1 reaction. Or there's other reactions that have similar properties that cause a scrambling or randomization of stereochemistry, and we call that racemization. All right, so that's the stereochemistry. So in the SN2 reaction, we actually flip the stereochemistry from wedge to dash based on the leaving group. But in the SN1 reaction, it ends up being 50-50 random wedge and dash after the reaction's over. B. Let's talk about the leaving group. The leaving group, same as SN2. Cutoff is F minus. So the same leaving groups that work in SN2 and E2 are the same for SN1. Specifically, iodine, bromine, chlorine, water, and sulfonate. Isn't that nice? We don't have to know anything special about the leaving groups in SN1. It's the exact same. Next, the nucleophile. The nucleophile, it's neutral, usually. And it's usually the solvent. You don't have to specify that. If you use a nucleophile and it's better if it's used as a solvent, I'll automatically assume you mean to use it as a solvent. You don't need to remember to say it's a solvent. I'll give you the credit there. Some common nucleophiles for SN1 include water. Basically, all the nucleophiles that are too poor for SN2. Alcohols, carboxylic acids, neutral phosphorus compounds like phosphines, and neutral sulfur compounds like thiols. Those all work fine for SN1. And remember that the choice of the nucleophile does not affect the rate, because it's unimolecular with respect to the substrate. You can use some negatively charged nucleophiles in SN1 reactions. It's rare, but not unheard of. We can see nucleophiles like acetate, so OAC minus, and then anionic sources of sulfur, anionic halogens like bromine, iodine, chlorine, have all been used in SN1 reactions, but you have to be careful. These anionic nucleophiles tend to be quite a bit stronger, and they can cause SN2 to predominate. So we'll look at how we can use anionic nucleophiles and still get it to go through an SN1 process versus SN2. And then in terms of the solvent, only thing you need to know about the solvent is that it must be protic. Although I will never have a reaction fail just because of the solvent, so never say no reaction just because the solvent doesn't seem to match what you're thinking. But just know that generally speaking in SN1 reactions, the solvent must be protic. And the reason for that is that they facilitate the dissociation step. So what the protic solvents do, if you remember, protic means that it can do hydrogen bonding. What protic solvents tend to do is they tend to hydrogen bond with the leaving group to help it dissociate. So you'll see hydrogen bonding interactions between the leaving group and things like the protic water molecules, which are acting as the solvent. And so we get these kind of polar stabilizing bonds, hydrogen bonds, which encourage dissociation. Protic solvents help leaving group leave because hydrogen bonding. And this is sometimes called solvolysis. When the solvent helps a dissociation step, that's sometimes called solvolysis. I think the textbook uses that word. I don't tend to use that word, but just so you're aware, solvolysis and dissociation basically mean the same thing. All right, now we're done talking about SN1. I just want to mention briefly what is E1. E1 is very similar to SN1. Let me show you, and then we're done. So the E1 reaction whenever you make a carbocation, E1 is possible. Let's take a look. So let's say we have this terbutyl bromide, great substrate for SN1. And we treat that with H2O. H2O is going to perform solvolysis and help the bromine dissociate. And we'll generate some carbocation. Okay, now the major pathway is SN1. It's multiple steps, nucleophilic attack followed by acid base, and we would ultimately end up with the alcohol as the product when water attacks and an acid base reaction occurs, and that's going to be our major product, SN1. But there's another pathway that's possible called E1, and the product of that is actually going to be an alkene. Okay, how does that occur? The mechanism of E1. Let's take a look. Okay, the mechanism of E1 is as follows. Same first step. Dissociation. So step 1 is dissociation. So same looking arrow. That gives us the carbocation. Looks like that. And now the second step of the E1 reaction is beta deprotonation. So let's draw in one of the beta hydrogens. There's lots of beta hydrogens in this molecule. I'm just drawing in one of them. The hydrogen that's on a carbon that's next to the double bond. And then some base comes in. We'll just abbreviate it with a B, and you can use B, but it could be water, it could be the bisulfite anion, anything. Just some weak base that's present is going to grab that beta hydrogen and then collapse that electrons towards the carbocation, making a double bond. Okay. And so this little B thing is a generic weak base. And it's actually kind of hard to probe what exactly this base is because there's so much solvent around, but it's believed to be just something reasonable for what's there in the reaction. So it can be water acting as the base. It could be the bisulfate anion, etc. Okay, so that is the mechanism of E1. You form the same carbocation, but instead of the nucleophile attacking the carbocation, the nucleophile does beta deprotonation, creating an alkene. Now, SN1 is typically favored over E1. But I'm going to make it super easy to know when it's E1. So always assume SN1, except you can force E1 with two conditions. H2SO4, heat. So if you see that, H2SO4 and heat, do E1. Or tosic acid, heat. Tosic acid is like sulfuric acid. It's toluene sulfonic acid. It's like sulfuric acid just with a toluene group. It's more soluble in organic solvents. So just look for either sulfuric acid and heat or tosic acid and heat. Those are going to be your red flags to do an E1 reaction. So let's take a look at example. Could have this alkyl halide. And we're going to treat that with H2SO4 and heat, which is sometimes abbreviated just with a triangle. So instead of writing out the word heat, they'll just draw that triangle, which is the Greek letter delta, which means heat. And the product is just going to be the E1 product, which is an alkene. Or let's take this substrate here. We treat that with tosic acid and heat. Again, I can use a triangle to represent that. And we're going to form the E1 product. Notice that we form the trans alkene if possible. And we're going to always form the Zaitsev, the most substituted alkene if possible. In other words, we make the double bond here versus here because we want it to be the most substituted, and we make trans over cis. Okay? So that's it. You know the E1 and the SN1 reaction, and the focus of tomorrow's lesson is going to be, okay, now how do we predict between SN2, E2, SN1, and E1? Because all four of these are in competition with each other. How can we decide based on the starting material and the reagents which reaction predominates, and then can we draw the product of that reaction? And once we do that, you're going to be in a really, really good spot moving forward in this class. I mean, you're basically going to understand the whole idea behind organic chemistry. It's all about looking at the starting material, looking at the reagents, predicting which reaction will occur, and then remembering what that reaction will do to the starting material so you can draw the product. And that's our ultimate goal, is to predict the outcomes of organic reactions. Once you do that, we can start building molecules that you want to build. So we can start stringing these reactions together and building things, connecting things together in interesting ways, and in a way we're going to be able to be creative when we construct new molecules. Okay? And that's the same technology that's used to create life-saving drugs today. So all those synthetic drugs that you see on TV, warning may cause side effects, blah, 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 blah. 99% of those are organic molecules. Actually, I'm not sure about that. Don't quote me. Lately, a lot of pharmaceuticals are not organic molecules, small organic molecules at least, but rather they are biologic, grown by bacteria. But a great majority of pharmaceuticals have been made in a lab synthetically using the reactions that we're going to learn in this class, or related reactions. Okay, we'll stop right there and we'll continue on this conversation next lesson.